Hey everyone, welcome back. We're going to start on we're going to do chapters 9 and 10 this week. Both of these are going to be covered on your exams, so you want to make sure you get through these before you take your test this week. The homework assignment's pretty straightforward. There's no discussion this week, so just make sure you go through these lecture slides really well, do the homework, review that if you need to, and then take that exam as soon as you feel you're ready. It's open until Sunday night. So we're going to start with Chapter 9. This is entitled Oceans, the Last Frontier. So we're just going to review some basics about the ocean. So technically, the Earth really has one big ocean with many features. All the oceans are interconnected. They're just divided up by arbitrary man-made boundaries. Earth is a blue planet. It is 71% of the surface is covered by oceans or seas. Only 29% is continents or islands, and the ocean is not evenly divided between the northern and southern hemispheres. The northern hemisphere is about 61% ocean. However, the southern hemisphere is 81%. And this is something I never really thought about. You don't realize how much of the continental landmass actually exists in the northern hemisphere. When you view the Earth from directly above the poles, where is the equator? So the equator doesn't run through the poles, right? The equator actually runs around basically the circumference of the Earth as we're looking at it from the poles. The world ocean is divided into four major ocean basins. The Pacific Ocean, which is the largest and the deepest. The Atlantic, which is second in area to the Pacific. The Indian, which is smaller than the Atlantic and exists mostly in the southern hemisphere. And the Arctic Ocean. It's about 7% the size of the Pacific, and it is the shallowest of all the oceans. The ocean has salinity to it. So seawater is salty, and this saltiness is expressed as salinity. Salinity is the term used to describe the total amount of solid material dissolved in water. Sodium chloride, also known as halite or table salt, is the major component, and it comprises about 85% of the dissolved solids in seawater. However, every naturally occurring element is found in seawater. Salt is an extremely valuable commodity. It is actively collected following seawater evaporation. It is solution mined, open pit mined, or tunnel mined throughout the world. So there are actually salt solution mines in New York State. The ones that I actually knew about, I didn't know about these ones up here in northwestern New York. I actually knew about the ones over by the Finger Lakes. These are these underground salt mines that were actively being used. There was debate about one of them being used to steal expelled or used up radioactive material from nuclear power plants. So when we talk about salinity, salinity is the total amount of solid material dissolved in water. This mineral content is expressed in parts per thousand. Average seawater has a salinity of 3.5%, also known as 3.5 parts per 100, or expressed in parts per thousand, this would be 35 parts per thousand. We don't really talk about it in percentages at that point. In every 1,000 grams of seawater, 965 grams of that is water, and then 35 grams of that are salts. When we say salts, that's just all the dissolved components, right? So in that 35 grams of salts, about 7.5% of it is my mind just blanked on what SO4 is. Excuse me. 3.5% is magnesium, 1.2% is calcium, 1.1% is potassium, 30.5% is sodium, and 55% is chloride. So where do these dissolved solids in seawater come from? They come from the weathering of rocks on the continent. So as these rocks weather, the rivers take this dissolved material into the sea. They can also come from volcanic activity. This provides minerals directly to the sea at hydrothermal vents and at divergent plate boundaries. And then on land, the volcanic activity provides minerals to the atmosphere during eruptions, and they eventually make their way to the oceans by precipitation. Ocean salinity has been stable for millions of years. So why doesn't the ocean get saltier with time? Dissolved minerals are removed from the water by precipitation of chemical sediments such as limestone or chert. So minerals removed from the water by plants and animals and are then used to build hard body parts. So the ocean can only contain so much dissolved solids. Okay, when it reaches basically a point of saturation, so about that 35%, it starts to precipitate it out. And that's where we get the buildup of the minerals in limestone. So it will deposit on the ocean floor and eventually undergo liquefaction and compaction to become a rock unit. Or it's uptaken by plants and animals that then convert that material to create shells or skeletons, such as types of snails, clams, oysters. This is a video on hydrothermal vents. I posted the link to this on Blackboard already. Please go ahead and watch this at your earliest convenience. Ocean salinity can be affected by varying amounts of fresh water available to mix with the ocean. This generally affects only the surface salinity. So processes that add fresh water and can temporarily reduce salinity are excess precipitation runoff from land, glacial and iceberg melting, and sea ice melting. Processes that would remove fresh water and increase salinity are excess evaporation. So changes in ocean surface salinities and temperatures are actually related. So if you look, salinity increases to a temperature of about 10 or 11 degrees Celsius and then drops down at the equator, and then it starts to increase again. So if you look, about 20 to 30 degrees off the equator, we start to see this significant increase in salinity. I already answered that question, sorry guys. So there are variations in the seawater temperature and density with depth. So open ocean can be divided into 3 layers. The shallow mixed zone, which is where waves and currents mix the temperature and salinity so they are uniform for their latitude. This is also the sun-warmed zone. So this general surface area right here. The transition zone, this is where very little mixing of water occurs and the temperature and water density change rapidly. And then the deep zone, which makes up about 80% of the ocean, this is where water temperature and density are uniform because sunlight never reaches these depths. So the transition zone is where you start getting that, very abrupt change of the warm surface. And as you go further down, you start to get cooler and cooler. Once you reach the deep zone, it's pretty, it's pretty well mixed. It's uniform, that's what I'm looking for. It's pretty uniform because of the lack of sunlight. So when we talk about the density of ocean water, density of a substance is determined by the amount of matter in a unit of volume. So common units for density are grams per cubic centimeter, grams per milliliter, or pounds per cubic foot. So density is just mass divided by volume. The density of a substance can be changed by packing more or less into a unit of volume. Okay, so if you want to pack more, and you're usually increasing pressure on your material to fit the same amount in a smaller unit of space. And then the density of a substance can be changed by increasing or decreasing the volume that contains the matter. So we know that the ocean space that contains the matter is not changing. So how does one change the volume of a substance, right? Because we already know the ocean size and shape is generally uniform. They're not changing by significant magnitudes. So to change the volume of our substance, we have to heat or cool it. The space between atoms expands during heating. So there's less matter in a unit of volume, which results in lower density. The space between atoms contracts during cooling. This causes there to be more matter in a unit of volume, resulting in a higher density. So as you have the warmer water up at the surface, there is less water molecules in 1 cubic meter of water, and so is less dense than the water in the deep ocean, where you have significantly cooler temperatures. So there's more water molecules in 1 cubic meter of water, giving it a higher density, and it's much heavier than the surface water. So ocean temperatures can actually be graphed with depth. The zone of temperature change is called the thermocline. So here we have the surface, about 24 degrees Celsius. And then we hit the thermocline, or the transition zone, and this is where we start to see a significant temperature decrease with depth. We reach that deep zone where the sunlight doesn't reach, and now we've got probably about 1,300 meters with depth. This is where we stabilize at our much colder temperature. Ocean density can also be graphed. The zone of density change is called the pycnocline. Now you can see here, these correlate roughly with each other. Typically the density changes much faster and much earlier than the thermocline does with depth. So why is a thermocline absent at high latitudes? Okay, so if you notice, we're starting with a surface temperature of about 22 degrees Celsius. When we're at the high latitudes, the polar regions, we're already at this extremely cold water temperature. So we don't have a thermocline here because there is no change in temperature with depth. You know, our water is uniformly just above freezing the entire way down. And then why is a pycnocline absent at high latitudes? Okay, so it's related to the lack of thermocline. This is because our water is not changing in temperature, so our density isn't changing because it's already colder, so that matter is already compressed into a space. So if you don't have a temperature-driven change in volume, you're not going to have any sort of change in density. We're going to look a bit at mapping the ocean floor. So bathymetry is the act of measuring the ocean depths and charting the topography of the ocean floor. So these are just some examples of some bathymetric maps and figures. Here's another YouTube video. Please watch as soon as you get a chance. There are a variety of methods used for mapping the ocean floor. You can use sonar, which stands for sound, navigation, and ranging. You can use echo sounding, a type of sonar. This uses the speed of sound waves in water to determine depth at single points from an echo of a sound transmission in the water. A side scan sonar provides wide sonic profile of the ocean floor, but not bathymetry. So it won't give us that topographic relief. A multi-scan sonar will provide both a narrow sonic profile of the ocean floor and bathymetry. We can also use satellites using radar altimeters. So radar stands for radio detection and ranging. Microwaves are beamed from a satellite to the ocean surface. Radar signals reflect back to the surface where the altimeter calculates the distance based on the time it takes the signal to get back to the satellite. Now this is a pretty cool method because the ocean surface is actually not flat, it's not uniform. The ocean floor highs have additional matter and so additional gravity. They attract more water to them than the surrounding lower areas, which cause a bump in the ocean surface above them. And ocean floor lows have less matter and so less gravity. They attract less water to them than the high areas, which cause a trough or a sink in the ocean surface above them. So we can actually use these rises and these sinks to get an impression of what the ocean bottom looks like, because it should generally reflect the ocean's floor. Okay, so this is just an image from your textbook of some of the ocean features that we have been able to measure using different bathymetric process. We're going to take a look at the Atlantic Ocean from this image. So here we're looking at a cross-section from, is that like north of Maine, it looks like, right near Maine, over to the coast of Africa. So if you look, The features are generally symmetric on either side of the mid-ocean ridge in the Atlantic floor. So here's our mid-ocean ridge, and it spreads fairly evenly in both directions. And each side has this passive continental margin. Okay, so we have our continental shelf, which is the very shallow water right off the coast. That's, this region right here. And then we get our continental slope and our continental rise, and then brings us down to our seamount. Seamount is slightly higher than the abyssal plains. These are basically those very wide, deep regions within the ocean. Before you start to reach the Rift Valley, and this is where you start to get those ridge series from that spreading zone. And then your mid-ocean ridge. And then it does the same back in the other direction. So that cross-section showed passive continental margins. Eastern North America and Western Africa both have passive margins. What this means is that the margin is tectonically inactive. There's no plate boundary there. No subduction, no seafloor flooding, no volcanoes, minimal earthquakes. A really stable place to exist. The East Coast, in terms of ground stability, is much more stable than significant areas or in California, for instance. So when we talk about the passive margin, we divide it into a shelf, a slope, and a rise. A continental shelf is a gently sloping submerged portion of the continent. So this is still primarily continental material. Our more felsic minerals make up this material. We've got sedimentary rock. Then we get our slope, which is steep, and it's the seaward edge of our shelf with a 5 to 25 degree slope. Finally, we get our continental rise, which is the gently sloping toe of the slope. So we get a decrease in that slope. So we go from, we can go from 5 degrees to 3 degrees, or 25 degrees to 10 degrees. And this is where sediment from the continent reaches this area through currents traveling down submarine canyons and form deep sea fans. In contrast, active continental margins exist along the Pacific Rim continents. These margins are tectonically active and have common subduction zones, and are located along active convergent plate boundaries and are subject to earthquakes, volcanic activity, and tsunamis. We talked a little bit about this when we talked about volcanoes. So the western coast of South America is extremely active. It has a large active volcano chain that's got a subducting or a convergent plate boundary. And when we have these convergent plate boundaries, we get deep ocean trenches. These are long, narrow troughs that make up the deepest portions of the ocean, and they are the least explored parts of the Earth. Here, pressures can exceed 16,000 psi, and for contrast, atmospheric surface pressure is 15 psi. So this is 4 orders of magnitude higher pressure at these depths. These form along active continental margins at subduction zones where oceanic crust is destroyed. So these deep ocean trenches and subduction zones are actually what make up what's called the Ring of Fire, which is the area of highest volcanic activity on the planet. And I mentioned the abyssal plains. These are deep, very flat plains that are covered in thick accumulations of sediment, and they are found in every ocean basin. They have a few hills and some undersea volcanoes, but they are fairly uniform. Here the water depth ranges from 12,000 to 15,000 feet, and these are the second deepest parts of the ocean. Then we get to the oceanic ridge system, also known as the divergent boundary zones. So these are extensive underwater, extrusive, or volcanic mountain ranges. They are the site of many hydrothermal vents because this is where we've got the continental crust spreading, and we have that melted lithosphere breaking through and creating new crust. This is actually one very long interconnected ring, and it is the largest continuous geographic feature on the Earth's surface, stretching over 40,000 miles. So this is just showing that extent of the ocean ridge system. And we've got a key here. So we've got some slower spreading going on in the mid-Atlantic ridge. It's not a very active spreading zone. Our fastest spreading zone is at the boundary of the East Pacific Rise and the Nazca Plate is one of those. So this is where we've got our most active spreading area, a pretty intermediate down between Antarctica and Australia. So the site of the seafloor spreading is, like we said, a divergent plate boundary and where new oceanic crust is created. This is where hot new crust is less dense than the surrounding rock, creating the higher ridge. The axis of this ridge may contain a deep, narrow rift valley created by the extension, a feature commonly found in divergent plate boundaries. So we have these very high ridges, but what you'll get is this very deep valley where the actual spreading and introduction of new crust material occurs. So like we said, sediments are thickest in the deep sea trenches, but they are present in all ocean provinces. There are three primary sediment types that accumulate on the ocean floor. You have terragenous, which is sediment from the land, biogenous, which are sediments from organisms, and hydrogenous, which are sediments from water. So terragenous are fine mineral grains weathered from rocks on the continents. So these are sediments that are carried down off the continental slope and shelves or off these active plate margins and down into these deep sea fans. They accumulate very slowly. You get about a centimeter of sediment over 1,000 years. The biogenous are shells and skeletal remains of microscopic marine animals and algae. Once the organisms die, their shells actually rain down and accumulate on the seafloor. And you can get two primary formations. You can get calcareous ooze, which are from calcite-rich shells, and siliceous ooze, which are from silica-rich shells. Finally, you get your hydrogenous sediments. These are minerals that crystallize or precipitate directly from seawater and form layers of chemical sediment. These are where you get calcium carbonates, such as your chemical limestones. Your manganese nodules, these are commonly found in your abyssal plains. You get metal sulfides at the hydrothermal vents, so those are those elements that are coming out of the gases within the Earth's interior. Or evaporates like halite, where there are shallow areas of the ocean that have restricted circulation and high evaporation rates. So this is just a calcareous ooze. This is formed from what are called foraminifera, or microscopic zooplankton. And then you get siliceous ooze-forming organisms, which are diatoms, or microscopic phytoplankton. Now, seafloor sediments can provide indirect evidence of past climates on Earth, and seafloor sediments can provide evidence of evolution of ocean life. Oops. There we go. They also have economic value if you can find a way to safely mine the ocean floor. Manganese nodules, copper, gold, cobalt, phosphorite nodules, and other rare earth elements are typically found from deep sea muds, and occasionally diamonds can be found in volcanic pipes on continental shelves. So here's a link for deep sea mining for rare earth. So that is the end of chapter 9's lecture. That was just a brief overview. So I'm going to move over to chapter 10 now. See if I can get this to pull up right in the middle of the video. Okay. Just bear with me for 1 second when we switch videos. There we go. Okay. So next we're going to go into chapter 10, the restless ocean. So here we're going to focus on ocean water movements. So ocean currents are basically masses of water that flow from one place to another. There are two types of ocean currents: your surface currents, which develop from friction between the ocean and the wind that blows across the surface, producing horizontal ocean movement, and deep currents, which develop from surface winds and density differences within the water column, producing vertical ocean movements. So our surface creates the horizontal movement, and the deep provide vertical movement. When we talk about surface currents, we also need to discuss gyres. A gyre is an ocean surface current that has a broad circular path and is driven by the prevailing winds in any given region. The surface of the ocean is actually divided into 5 main gyres: the North Pacific Gyre, the South Pacific Gyre, the North Atlantic, the South Atlantic, and the Indian Ocean. The gyres rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere due to the rotation of the Earth, which creates the Coriolis effect. And we'll address that more in a few weeks. So, this is an image of the 5 gyres. Each gyre has 4 main currents. The red are the warm currents, and the blue are the cold currents. In the southern hemisphere, though, the west wind drift is the only current that circles the entire globe. The east wind drift is the southernmost ocean current. So if we look here, we have our South Pacific Gyre with our cold water coming from the west, hitting the western coast of South America and moving upwards, warming at the equator, and then moving back westwards before it moves down along the eastern coast of Australia. Our North Atlantic Gyre cycles from the equator up towards North America and Greenland, and as it comes into contact with Ireland and the UK, it starts to cool and cycle back down towards the equator. You actually get a bit of an offshoot of the North Atlantic Gyre up here between Greenland and the Slavic countries. And our Indian Ocean Gyre, and it actually has 2 warm water offshoots up between Saudi Arabia and India, and then between India and Thailand, Vietnam. So this is just showing how the wind currents cycle and how they impact the gyres. So you see the wind cycles in a clockwise manner in the northern hemisphere, causing that clockwise water movement. In the southern hemisphere, it goes in the other direction, causing that counterclockwise movement. The currents redistribute heat toward the poles from warm areas and bring cold water down towards the equator. These gyres actually influence continental climates. The warm water currents increase the temperature of the air above them, causing the air to rise and increase precipitation over the lands. And the cold water currents decrease the temperature of the air above them and cause the air to sink and decrease precipitation over adjacent lands. Okay, when we talk about upwellings, this is the rising of cold waters from deeper layers of the ocean to replace the warmer surface waters which have moved away. And this is because of the wind movement. And then coastal upwelling takes place along the west coast of some continents, Western North America, South America, and Africa specifically. So this is where your wind is blowing your surface water away. And as that goes, you have the upwelling of the cold water moving up to the surface here. Denser water sinks and less dense water floats on top of it, like we addressed in Chapter 9. And the changes in water temperature and salinity can cause changes in water density. So we talked about how temperature changed water density, but now let's address how salinity can cause changes. So salinity affects water's density because as you increase the solids within, the dissolved solids within a water, you're actually increasing the amount of molecules that are contained within that same space. So even though, like, I dump a whole bunch of salt in, and even though it doesn't look like our water has changed, that salt has just been dissolved, you're now increasing the amount of molecules within the same space. So vertical movement of water due to changes in its density by salinity or temperature are called thermohaline circulation. And most deep ocean currents begin in the polar regions where the salinity of the water varies as sea ice forms on the surface of the ocean, resulting in saltier ocean in that area. So as you get that sea ice forming, the water will freeze and it will not bring those dissolved solids with it. So you're removing water and you're increasing the salinity of the water that's left because of that. So these dense, higher salinity waters sink and then flow towards the equator in the deep ocean. So here we're looking at what's called the conveyor belt model of ocean circulation. So we have our warm waters, and as they come here and start to cool, you get that formation of the ice, and the waters cool, and they have that increased density, and they start to flow back down towards the equator. And you actually get this kind of crossover movement because they're much denser than the warm water, right? So they continue to flow down. And then the currents begin to move that cold water back up where it warms around the equator and starts to flow again over the surface. Shorelines are a dynamic interface of these interactions between air, land, and sea. Some of the dynamic forces along the shoreline are waves, winds, erosion, tides, currents, and precipitation. Okay, so there are a lot of factors that can really impact the environment found in a coastal region. So what is happening to human populations in the dynamic shoreline environment? So if you have a shoreline that is undergoing erosion or high energy currents, lots of precipitation, these human settlements are not very stable. They have a lot of typhoons or hurricanes. They have a lot of high water events, a lot of destruction because we're building on regions that are climatically very unstable and not really suitable for long-term habitation. Oops. Even so, if you look, you have the coastal regions are some of the highest density areas along or within the U.S., especially right along the West Coast, California, and even in the eastern states. In Florida, Pennsylvania and New York are both fairly populated states, and there's a lot of fresh water available, but you still have clusters of populations right along this shoreline here. So when we look at these dynamic forces and their impact on shorelines, first we want to look at ocean waves. So what are waves? We talk about them, we go to the beach, oh, there's a lot of waves today, there's high waves today, there's not a whole lot. Waves are just the energy traveling along the interface between the ocean and the atmosphere. They derive their energy and motion from the wind. So the wind is really what's giving the energy to this movement at that boundary. There are two parts to the wave, the crest, which is the top of the wave, and the trough, which is the lowest part of the wave surface between crests. And we will examine those in a little more depth soon. And then some wave characteristics we'll talk about are the wave height, which is the distance between a wave trough and a crest, and the wave length, which is the horizontal distance between two successive wave crests. So we'll have a crest, then a trough, and then another crest, and this is your wavelength. And the wave period is the time interval for one full wave to pass a fixed position. So you have your wave cresting and how long it takes to get past that and your next crest to hit that same point. That's your wave period. So here's a diagram of a wave. So we've got our crest and our trough, and our wave height is that height difference between the high and the low. And our wavelength is the distance between one crest to the next crest. Okay. And wave height, wavelength, and wave period are controlled by the wind speed, the length of time the wind has been blowing, and the fetch, or the distance over which the wind has been blowing. So how much energy is building up within that water. And we'll go into some of the other things pointed out in this figure in a little bit. Waves can travel great distances, but the water itself does not. The water particles move in a circular orbit motion and stay relatively fixed compared to the wave motion of the water surface. Now, this is a really good video link to show how those particles move in that circular motion but stay essentially stationary as these waves progress. Now, there are changes that occur when a wave moves to shore. So what happens is we have these particle orbits, and as you have the wave energy or the wind energy coming, you have much larger orbital circles for the particles towards the surface. But as you increase with depth, you're not getting all that energy transfer from the wind, so you have smaller orbits with these wave particles or water particles until you reach a point where there is no impact from the wind. So once you reach a depth that is 1/2 your wavelength, so remember, here's our wavelength, one crest to the next. If we go to a depth equal to 1/2 our wavelength, the wind has no impact on our water molecules, and you will get no water movement due to waves at this depth. Now, as you start decreasing this depth, so as you reach shore, You reach a point where the waves are still, so here the waves kind of terminate, there's no wave, but here our waves are actually still moving as we hit the Earth's surface, right? So as they start to encounter the water depths, that bottom friction with the seafloor causes the top of the wave to move faster than the base because you've got increased friction here, right? So these are still moving, but it's not moving as fast down here. It's getting dragged along the bottom now. And it keeps dragging, and it changes these circular orbits into elliptical orbits, which cause these like increased wave crest until eventually you get to a point with a surf zone where you get these breakers forming, and then the top of the wave becomes so unstable because, if you look, it's not balanced throughout. Here it's balanced throughout its column. It's not balanced throughout its column anymore, so as it reaches that surface, it becomes unstable, and the top of that wave crashes down, creating a breaking wave or a breaker. So as we're talking about water approaching the beach is just the sediment accumulation at a shoreline. These sediments are composed of whatever is locally abundant, and they don't stay in one place as the waves move it. So beaches may be long and linear or restricted to quiet waters along irregular shores. So this is an example of a beach on Florida's, I think it's Sanibel Island, and this is primarily shells and shell fragments. And here are the black sands, a black sand beach in Hawaii, derived from the weathering of those nearby basaltic lava flows that bury mafic material. Now, beaches and shorelines undergo significant wave erosion. This is where large high-energy waves or medium-sized waves over a long period of time cause significant shoreline erosion. This is caused by either the wave impact, abrasion by rock particles within the wave, or dissolution of certain rocks, such as limestones that are rich in calcite, by the acidic ocean water. The Atlantic Ocean storm waves can actually generate forces exceeding 2,000 pounds per square foot. So this is just a time lapse of the erosion of a shoreline in Alaska. And here's another coastal erosion video, so please watch these on your own time. So how does the sediment or sand move from this wave-driven erosion? So sediment moves perpendicular to the beach. So if you have the erosion occurring when the wave backwash energy, so you have a wave and your backwash is when that water moves back to the ocean, is greater than the wave swash energy of movement forwards. You get wave refraction, which is the bending of waves by shoreline irregularities, which affects the energy distribution of the waves and how sand is moved. And it can create different erosion rates. So you can get wave energy concentrated on headlands, so it increases erosion. Or you can have the wave energy as the wave goes into a bay. So as it goes into a bay, it actually loses energy because you're going from a narrow opening to a wide opening again. You get less erosion. And then it eventually straightens out in a regular shoreline based on this change in distribution of high energy and low energy areas. One of the most common ways that sediment is moved, though, is longshore transport. This is where sediment moves in a zigzag pattern along the beach face. The longshore current is the current in a surf zone that flows parallel to the shore, resulting in sediment movement down the shoreline. Oops. So here's an example of wave refraction. So you've got the water coming in, and it's hitting this headland first, and so it's warping that wave movement as it comes to the headland, and it hits, and it's bringing everything into that headland because you're slowing that velocity as it hits this. Whereas if you have water coming into a bay, as it comes around this area, all of a sudden it's got this nice open area to expand into, and the waves bend outward, giving you lower energy and less erosion. So here's a good example of longshore current. So what happens is if you've got wind blowing, you don't have your water moving straight at your beach. You've got it moving at an angle to your beach. So the waves come in at an angle, but the sand always moves out perpendicular. But then you've got a wave bringing it up at an angle and out perpendicular. So it pushes it down the beach and then pulls it back off the shore, carrying the sand at an angle up or down the beach. And these waves approach the beach at a slight angle, moving the current from left to right in this image here. You see if they hit at an angle up here and they'll float back down, and they'll hit at an angle here and float back in. So this is a good video example of longshore beach drift. Sorry, watch this one. There are a number of erosional shoreline features that are good evidence of historic oceanic activity. First are wave-cut cliffs. These are erosion that creates a sharp cliff face at a shoreline which retreats toward land. So these are wave-cut cliffs. You get a wave-cut platform, that's this right here. This is the flat submerged surface left behind after erosion and removal of a wave-cut cliff. So at some point, the ocean level was at least to here because it only eroded the material at the surface up to here, leaving this platform there. You can also get a marine terrace. This is where a flat surface above sea level formed when land is uplifted or sea level drops, exposing a wave-cut platform. Okay, so this used to be a wave-cut platform before there was some sort of tectonic or climactic activity that changed the sea level there. Headland erosional features tend to be formed of more resistant rock than adjacent bays, and because of this, they form some unique structures. Most common are sea arches, which is just the erosional joining of two sea caves that leave an arch. So here's a sea cave, and eventually it will break all the way through, causing an arch. And then sea stacks. These are the pillars that are left after the collapse of a sea arch. So here's how far our landmass originally extended. And it underwent active erosion. At one point there was a sea arch here until the roof of it became so unstable it collapsed, leaving a stack. And then we have that same activity occurring as we move further in along that cliff formation. We also have some depositional headland features. These are sediments deposited by longshore currents, and many of these features occur if the wave energy in an area is low. First are sand spits. These are elongated ridges of sand that often hook into a bay. So we've got this low energy. It's moving all this sand down the beach until it starts to accumulate at the edge of the beach here. It starts depositing this low energy up into a bay region. We have a bay mouth bar. This is the sandbar that crosses a bay, completely sealing it off from the open ocean. So if this extended all the way across, we would get a bay mouth bar. And then a tombolo, which is a ridge of sand that connects an island to the mainland. So you have this area of lower energy, so you start to get deposition of sediment instead of erosion here. Okay, Lake Erie and Presque Isle out by Erie, Pennsylvania. Presque Isle is actually a really good example of a spit. This is a deposition of sand that occurred from the currents within Lake Erie that have created this nice spit right outside the city. And Long Point, Ontario is another spit. So here's Presque Isle. It's this teeny little spit in Lake Erie, and then Long Point, Ontario, it's a much larger spit. But you can kind of see evidence of this material being moved down in this direction and depositing. You can also get barrier islands. These are thin, low ridges of sand that are parallel to shorelines, and they can extend for hundreds of miles. They're extremely common on the Gulf and Atlantic coast. You get dunes, which are wind-drifted sand hills. They tend to occur on barrier islands or along the beaches of your mainland, and lagoons, which are thin bodies of water that separate the barrier islands from the mainland. So shoreline erosion is influenced by your proximity to sediment-rich rivers, the amount of tectonic activity you have, the topography and composition of your land. So if you have the more weather-resistant rocks, they're not going to erode the same way that a limestone or shale would. Your prevailing wind and weather patterns and your shape of your coastline. Shoreline erosion can also be modified by artificial means such as hard stabilization or beach nourishment. So when we talk about hard stabilization, these are building structures. These are man-made features that try to reduce the amount of erosion that occur. You get groins, which are barriers that are built at a right angle to the beach, and they're designed to trap sand. Sand will build up behind these. Breakwaters are built parallel to the coast, much like a barrier island, and this is to protect boats from breaking waves. And then seawalls, which are armored armor the coast against the force of breaking waves. So these are built up along the actual coastline to reduce erosion from the ocean. The structures are expensive and they're not always effective. Even if they do what they're built for, a lot of times they can have negative consequences that weren't foreseen and have large impacts down the coast. So here's some pictures of some groins. So you see they come out at a right angle from the beach, and so you get sediment accumulation behind the groin. Here's a seawall in Galveston, Texas. So they just built a concrete wall to make sure that there is no erosion occurring and reducing the shoreline. Here's a breakwater that was built outside Buffalo, New York. Okay, so the waves off of Lake Erie would not impact these boats. And here's some breakwaters that are actually built outside of Dunkirk. However, these activities can cause us to have to do some additional features, such as beach nourishment. This is adding sand to the beach because there's been significant erosion and the beaches have been eroded to basically nothing. But this is not a permanent solution. It's not solving the problem of why there's such a high rate of erosion. The other method is the removal of these man-made structures and buildings, allowing nature to reclaim the beach. So a lot of these areas where you have such high rates of erosion of the beach, it's because up current of the beach, there's been some man-made structure to keep sediment from moving from up there down the beach. So all of a sudden it's all accumulating here and you're depriving the beach region here, so all that energy from the water is now scouring and eroding that region too. So if we remove these structures like the groins or the breakwaters, it can actually eliminate the need to do the beach nourishment and allow it to proceed at its equilibrium state. The problems are different along opposite coasts. The Atlantic and Gulf coasts, you have development that occurs on barrier islands. These face the open ocean and receive the full brunt of storms that occur. Unfortunately, development has happened more rapidly than our understanding of the dynamics here, so we had a lot of population and settlement on these islands before realizing that basically any storm that comes in is going to create significant damage to human health and livelihood and buildings. On the Pacific coast, you have relatively narrow beaches that are backed by steep cliffs and mountain ranges. And a major problem is the narrowing of these beaches. So the sediment for the beaches is typically carried in the rivers, but it is interrupted by dams and reservoirs. These dams and reservoirs are becoming what are called sediment sinks. All the sediment is staying here and getting trapped within these regions of the river system. It's not being carried down to the ocean. And because you don't have this constant regular introduction of sediment, you have a much higher rate of erosion of the sediment that is on these beaches. There are two types of coastlines. You have emerging coasts. These are created by the uplift of land or the drop in sea level. And submerging coasts. These are irregular shorelines with estuaries, which are what we call drowned river mouths, created by the subsidence of the land or a rise in sea level. The Chesapeake Bay is a really good example of a submergent coast. These are all river systems that feed into the Chesapeake Bay region that are now submerged and contain brackish water because as ocean levels rise, it starts to back up that water into those river systems and river valleys. And it's important to note that coasts may shift from emergent to submergent and back again based on the plate tectonic dynamics or the dynamics of climate and its impact on ocean levels. So we're going to look at some emergent and submergent coastline features. Here are some emergent coastline features. We've got an active beach, our wave-cut bench, or our shallow water area, and our historic sea level. And then as time goes by, our sea level drops, and all of a sudden we've got this exposed wave-cut bench, where we have that active wave activity going on. And we have a new active beach that has been eroded down, and our new wave-cut bench. Here we have an example of a submergent coast region. Sorry, guys. So you can see our rivers moving down their valleys. You have your depositional alluvial fans here as it moves through the ocean system. As time time goes by and the ocean level rises, it starts to flood these river systems and drown the valleys up towards their headwaters or headland areas. Now, we're talking about this, we also need to address ocean tides. Ocean tides can change the elevation of the Earth's surface. This is caused by gravitational forces upon the Earth of the Moon and to a much lesser extent the Sun. The Moon's gravitational force creates two tidal bulges on the Earth, one on the side of the Earth facing the Moon and the other on the opposite side of the Earth. So the Earth rotates beneath the tidal bulges, resulting in two high tides and two low tides each day from any shoreline location on Earth. So how do tides work? This is a really great video just kind of explaining the basics of ocean tides, so please make sure you take the time to watch this. The tidal patterns can be influenced by many factors. You've got your shape of the coastline, configuration of your ocean basin, and your water depth. There are three main tidal patterns. Your diurnal, which is down here, your single high tide and low tide each tidal day. So from 0 to 24 hours, we have a high tide and a low tide, and a high tide and a low tide. You have your semi-diurnal, which are two high tides and two low tides each day. So just a more compact and amplified pattern. And then you're mixed. These are like semi-diurnal, but the water levels vary during the tidal cycles. Okay, so you would have, say this was 6 a.m. So 6 a.m. was always a much lower low tide than the 6 p.m. low tide. The tidal currents are horizontal flow, accompanied by a vertical rise and fall of the tides, and the currents can range from slow to very fast, depending on the shore. You can also get a flood current, which is the advance towards the coast, and the ebb current, which is where it recedes from the coast. And these currents produce unique shoreline landforms, such as tidal flats. These are zones that are affected by the alternating high and low tides, and are usually preserved where the shorelines typically have very low wave energy. So there's not a whole lot of active erosion going on. And then your tidal deltas. These are areas of sediment deposition associated with a barrier island inlet. You can get your ebb tidal deltas or your flood tidal deltas. So here we have our tidal flats. So these are areas that are impacted with the rise and fall of the tides. And we have our lagoon here behind our barrier island. And we have what's called a tidal delta that develops, and it's because it's developed as the tide moves into land, or on the landward side, it's called a flood delta. So it is caused by the flooding of your coastline at